Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to talk about how to relate the standard Gibbs free energy and the electropotential of a cell. And so we're going to do a couple of example problems where we're given a couple of equations and a couple of redox reactions, and we're going to go step by step to get to the Gibbs free energy, or the standard Gibbs free energy for this reaction, or for these reactions. So first thing you need to do is to figure out the electrochemical potential of this reaction, which means that you're going to have to use the standard electrode potentials. So we're going to use this equation here. So the standard electrochemical potential of the cell is equal to the electrode potentials, the difference in the electrode potentials. So it's the electrode potential of the cathode minus the electrode potential of the anode. Now, once you get the standard electrochemical potential of the cell, now you can plug that into this equation with Faraday's constant, and you can get the standard Gibbs free energy of this reaction. So let's start with number one. So the first thing you want to do is you want to break this up into its two half reactions, the reduction and oxidation half reactions, and then you can get the tabulated, look up the electrode potentials in a table. So that's what we're going to do. So the first one, we have I2 solid goes to 2I negative. Okay, so this is going to be gaining electrons. So we're going from 0 oxidation state to -1. So we're going to add 2 electrons, and then that's going to go to 2I minus aqueous. And then we have the 2 Br minus aqueous. That's going to lose 2 electrons, and that's going to be Br2 liquid plus the 2 electrons. And so this is gaining electrons, so that's going to be reduction, oil rig. Remember, oil rig, reduction is gain of electrons, so this is reduction. So reduction. And this is oxidation, oil. Oxidation is loss of electrons, oil. So we're losing electrons here. This is oxidation. Oxidation. And so if we look up the electrode potentials for these reactions, so for this one, for the oxidation at the anode, it's going to be 1.09 volts. So at the anode here, this is, what did I say it was? 1.09. So the standard electrode potential at the anode is going to be, let me look at it again. Sorry, 1.09. 1.09 volts, and this is going to be the cathode. So this is at the cathode, and the standard electrode potential of the cathode is going to be equal to 0.54. So 0.54 volts. And so if we subtract cathode from anode, so we subtract the 0.54, so the cathode, we're going to take the cathode here, cathode 0.54 volts minus 1.09. So if we do that up here, so the electric potential of the cell is equal to the cathode minus the anode, which is going to be 0.54 volts minus 1.09 volts. And that's going to give us negative 0.55 volts. Okay, so now we have the electropotential of the cell, negative 0.55 volts. Now we can plug that into our equation here. And so the way we do that is we're going to, there we go. I'm going to go ahead and erase this now so we can get some more room here. Okay, so we're now going to use our equation here. So we're going to use the delta G, standard Gibbs free energy, is equal to N. N is the number of moles of electrons that are being transferred times Faraday's constant multiplied by the standard electrochemical potential of the cell. So this is going to be 2 electrons. We're transferring 2 electrons. So that's going to be 2 moles, right? This is going to be per moles. And then we got Faraday's constant, which is going to be 96,485. So let me fix this a little bit here. So we got 2 moles of electrons that are being transferred. And this is 96,485. So 485. And that's going to be coulombs per mole of electrons. And then we're going to be multiplying that by the voltage. And remember, voltage is joules per coulomb. So 0.55, negative 0.55 joules per coulomb. So, and the reason is that is because a volt is joules, energy per coulomb. Okay, so moles of electrons cancels out, coulombs cancel out. Now we have joules. That's going to be our Gibbs free energy in joules. So all we have to do is calculate that out. And we calculate it out. And it's a positive 1.1. So this equals positive 1.1 times 10 to the 5th, I believe, 5th joules. So positive 5 joules. And so now, now that we have our Gibbs free energy, we can say whether or not this is going to be spontaneous. So in a previous video, we were able to look at the comparison between the electrode potentials of the reduction half reactions of your redox reaction and figure out whether it's going to be potential or it's going to be spontaneous that way. Here, we're using the Gibbs free energy, the change in the Gibbs free energy, to say whether it's going to be spontaneous or not. And if you remember, positive changes in the Gibbs free energy means that it is not spontaneous. So here, this would not be a spontaneous redox reaction. Okay, so what about the next one? So again, we are going to write out the half reactions. So the half reaction of sodium, so we have sodium solid. So it's going to be 2 Na solid. And that's going to go to 2 Na plus. So that means it's going to lose 2 electrons. So 2 electrons lost. So plus, let me write this in the normal way. So this is going to go to 2 Na plus. plus 2 electrons. So 2 electrons are being lost. Okay, and so here we have water, which is no oxidation states of water, or at least the oxidation state of oxygen is -2. That's going to be a +2. Here, the oxidation state is 0. And again, here, oxidation state here is going to be +1 and -2. So that's going to be a total of -1. So nothing oxidized here. So it looks like hydrogen is going from a +1 to a H2 plus. So when we write that down, we're going to have 2 water, 2 H2O liquid is going to H2 gas plus 2 OH minus, and then that's going to be going to, let's see here. And so here, since this is becoming negative, let me fix this. So we're going to gain 2 electrons there. And so here we have the 2 half reactions. So here we're losing, so this is going to be oxidation, and that's going to be happening at the anode. And here we're gaining electrons, so this is our reduction. This is going to be happening at the cathode. So we look up the reduction, we look up the electropotentials for those, and we get, and so the electropotential for the sodium is -2.71. So this is, okay, this is 2.71. Is that negative? Where's sodium go? Yeah, negative 2.71 for the anode. I'm sorry, for the cathode. For this reaction with water, that's going to be -0.83. -0.83. Okay, so volts. And so to get the standard electropotential of the cell, cathode minus anode. So here, electropotential of the cell is equal to the cathode minus the anode, so -0.83 minus -2.71 volts. Okay, so we do our calculation. Okay, and so the electropotential of the cells is going to be equal to a positive 1.88 volts. And I just realized over here I forgot the negative here. And so the negative there, that's why this is positive for anyone who might have been wondering about that. All right, so now I just plug this into the equation. So same equation here. Delta G standard is equal to -N times F times the electropotential of the cell. And that's going to be the number of moles of electron is 2 again. So that's going to be -2 moles of electrons times, again, this Faraday's constant, 96,485 coulombs per mole of electrons, multiplied by positive 8.88 joules per coulomb.